Oh, it worked out. So today we're going to talk about sample surveys, right? So we've learned ways to describe and display and summarize data, but we've been limited to examining a particular batch of data that we have. So to make decisions, we need to go beyond the data at hand and to the world at large. So we're going to look at three major ideas that will allow us to make this stretch. First idea is to draw a sample. We like to know about an entire population of individuals, but examining all of them usually is impractical and impossible. I can't figure out the height or weight of every human being on planet Earth, so I take a small sample. We settle for examining a smaller group of individuals or a sample selected from the population. Sampling is a natural thing to do. Think about sampling something that you're cooking. You taste or examine a small part of what you're cooking to get an idea of how the whole dish will taste. Opinion polls are examples of surveys designed to ask questions of a small group of people in the hope of learning something about the entire population. Professional pollsters work quite hard to ensure that the sample they take represents or is representative of the population. If not, the sample could give misleading information about the population. We see this a lot in political polls too. So whenever there's an election, by the way, tomorrow's election day, whenever there's an election, they say the polls say this, the polls say that, and sometimes the polls aren't right. There's a lot of things that go into that, and we're going to start talking about how to collect a good sample. So sampling methods, by their nature, tend to over or underemphasize some characteristics of the population that are said to be biased. So bias is, it has a lean one way or the other, all right? There's usually no way to fix bias, okay? Although you should try very, very hard. The best way to avoid bias is to select random individuals for the sample at random. So bias is a real thing. In a political poll, we have two political parties. It depends on how you want to do it. There are some geographic locations that are predominantly Republican. There are other geographic locations which could be like a neighboring town that is Democratic. And if you wanted to conduct a survey of how somebody's going to vote or their opinion on policy, it'd be a good idea to sample both cities and have a sample from both. But you want to do it randomly because it doesn't, it's interesting because if you only sampled one city, you would lean one way or the other. So that's what we're trying, and that would be what we would call a bias, right? The whole point of everything we're going to talk about today is a random sample that will give you an accurate prediction about what the population may do. And that doesn't just refer to people. We could talk about science and samples in science. You can sample feeding times of birds. You could sample tensile strength of materials. You can sample lots of things and then apply that to the total population based on those parameters. But the value of deliberately introducing randomness is one of the great insights of statistics. So randomization can protect you against factors that you know are in the data. It can help protect you against factors you are not aware of. So I said specifically that we're going to sample from both towns, but even that could show some bias. Randomizing protects us from the influence of all the features of our population, even the ones that we may not have thought about. Randomizing makes sure that the average sample looks like the rest of the population. Not only does randomizing protect us from bias, it actually makes it possible for us to draw inferences about the population when we see only a sample. Such inferences are among the most powerful things we could do in statistics. But remember that it's all made possible because we deliberately choose things randomly. How large of a random sample do we need for the sample to be reasonably representative of the population? Well, it's not the size of the sample, and it's not the size of the population that makes the difference in sampling. There is an exception, though. If the population is small enough, the sample is more than 10% of the whole population, the population size can matter, right? So if I got, 7 kids in this class today? If I wanted to sample half of you, let's say I sampled 4 people, that's well over 10%, but 10% of 7 is not even a whole person, right? So I can ask the opinion of 1 kid in this class, and it doesn't necessarily reflect the opinions of the entire class. So that's what they're talking about. Now, if you have a compare that to the number of students we have in this school, and I sample you 7 kids, you're not representative of the whole school. So that's why we got to consider those things. A fraction of the population that you sample doesn't matter. The sample size itself, though, that's important. Generally, most textbooks say you want to have more than 40 or 50 people. So why bother determining the right sample size? Well, wouldn't it be better to just include everyone and the sample the entire population? Well, such a special sample like this is called the census. So the census is a little thing that we send out to every household in the United States. It's done, I think, if I remember correctly, every 10 or 20 years. And they just ask random information, and they update it. I have never filled out a census form. It's just too much work. I'm too busy. I don't care. And I'm sure there's probably some other people like that. So it's a sample in the sense because they're trying to collect information from everybody. And people will show up at your house and say, we noticed that you didn't fill out a census. And they'll try to fill it out right then and there. But that's okay. They're just trying to collect data and information so they can make adjustments. You'll hear the advertisement, and it helps us to determine how we spend money, how we consider where to allocate resources to different parts of our population. So it's a great example of a large sample. There are problems with taking a census, though. It can be difficult to complete a census. There always seem to be some individuals who are hard to locate and hard to measure, or it may be impractical. Food is like kind of an example, like how much food does somebody need or use or have. Populations rarely stand still. Even if you could take a census, the population changes while you work, so it's never possible to get a perfect measure, right? I could have moved in the middle of the census. It takes months, almost a whole year, to complete the census in the U.S. So I could move, I could change jobs, I could have a birth, I could experience a loss. So all those things take place. So then the information is not, from a practical perspective, up to date. Populations really stand still, as I mentioned. Taking a census may be more complex than sampling. I could execute a small sample of the population far more quickly than I can. And by the way, if it's a good sample, the inferences that we can make about the population should be very similar. Models use mathematics to represent reality. Parameters of the key numbers in those models. A parameter is a part of the model of the population. It's called a population model or a parameter. So I'm gonna just pause the notes for a second. Sample is referring to the information that we've collected. It's a small portion of the population. Whenever we refer to population, we're talking about the big thing. Whether it's people, tensile strength, how many flowers there are, we're talking about every tulip, right? Am I going to go and measure information on every tulip? No, I'm going to collect a small sample. But we have sample variance and we have population variance. We have sample standard deviation, we have population standard deviation. If we toss that word population in front of it, odds are it is a prediction. If we say sample in front of whatever the parameter is, it is from an actual sample and real data. Okay, so keep that in mind as we forge forward. We use data to estimate population parameters. Any summary found from the data is a statistic, and statistics is an estimation population parameters called sample statistics. Okay. I just erased this from the board, which is ironic, but just so you know, we typically use Greek letters to denote parameters and Latin letters to denote statistics. So they switched up a little bit. Now, Latin letters are what you guys are used to, right? Regular letters. So mean, Y bar, for a statistic is Y bar. But for a parameter, it's mu, the Greek letter mu. Standard deviation, regular letter S. For a parameter, it is sigma, Greek letter S. Correlation, R, so we say R squared. But for a parameter, we use the Greek letter for R, which is rho, which kind of looks like a P. Regression coefficient, we just say B, but for a parameter, we say beta, capital letter beta. Proportion, P hat, and then parameter, it's actually P. Okay? So keep that in mind. We draw samples because we can't work with the entire population. We need to be sure that the statistics we compute from the sample reflect corresponding parameters accurately. A sample that does this is said to be representative. Okay? We will insist that every possible sample of the size we plan to draw has an equal chance to be selected. That is a little more complicated than you think. If we were to look at, say, ethnicity in the United States, there is a certain percentage of people that are Caucasian, there's a certain percentage that are African American, Latino, Asian, mix of those heritages. And so we can go through and do a random sample, but sometimes they do a random sample and try to, and it's not as random, but try to be representative of everybody, okay? So such samples also guarantee that each individual has an equal chance of being selected. Well, that's something that you want to consider for total randomness, all right? Color of marbles in a bag. If I have 40 blue marbles and 3 red marbles, and I take a random sample, I'm going to get more blue than red. Does that make sense? So a lot of times we want to try to figure that out too. With the method, each combination of people has an equal chance of being selected as well. So even though I've got more red and blue or whatever the proportions are, if I replace all the marbles every time, it's totally random. So that's where they're going with this. Even though the numbers don't match up, if I'm just closing my eyes and reaching in the bag, I'm going to have an equal probability of selecting a marble, but it depends on the parameters that you're trying to, or not parameters, the inferences you're trying to make. So a sample draw in this way is called a simple random sample. So if I have the same number of red marbles, the same number of green marbles, the same number of blue marbles, I could just randomly do it because I have an equal probability of selecting any color. Okay. In SRS is the standard against which we measure other sampling methods. Okay. So the sampling method on which the theory of working with sample data, is based. All right. So to select a sample at random, we first need to define what the sample will come from. The sampling frame is a list of individuals from which the sample is drawn. Once we have our sampling frame, the easiest way to choose our SRS is to assign a random number to each individual in the sampling frame. Samples drawn at random generally differ from one another. Each draw in random numbers selects different people for our sample draw. These differences lead to different values for the variables we measure. We call this sample-to-sample differences sampling variability. Simple random sampling, or SRS, is not the only fair way to sample. So basically what I would do, let me back up a second. I'd give each one of you a number. You're number 1, you're number 2, you're number 3, 4, 5, 6, 7. Then I use a random number generator, and that's how I select you. So if I wanted to draw 3 students from this class, I would assign a number to you, and then I would use a random number generator to generate 1 to 7 without replacement, and I would pull 3 kids based on the numbers that were drawn. More complicated designs may save time and or money or avoid sampling problems. All statistic sample designs have in common the idea that chance rather than human choice is used to select the sample. What they're saying by total randomness and bias is by using the random number generator, I'm not thinking about it. So I might think to myself, well, I want to make sure I have 1 girl, and I want to have 1 boy, and I want to have 1 ethnicity or another. I'm choosing. I think that it's being unbiased. I think that I'm being totally random, but I'm not. By assigning number values to you and letting the calculator pick the numbers, it's totally random. Designs used to sample from large populations are often more complicated than simple random samples. Sometimes the population is first sliced into homogeneous groups called strata before the sample is selected. Then a simple random sample is used for each strata or stratum before the results are combined. This common sampling design is called stratified random sampling. So this is a great example. If I want to look at ethnicity in the United States, I put people in categories, right? And then I randomly choose from each category. Now the category in statistics is called strata. Okay. The most important benefit of stratifying can reduce the variability of our results. When we restrict by strata, additional samples are more like one another, so statistics calculated from the sampled values will vary less from one sample to the other. Strata random sampling can reduce bias because we get an equal representative of the different strata. And then stratified sampling can also help us notice important differences among the groups. Okay. Sometimes stratifying isn't practical and simple random sampling is difficult. Splitting the population into similar parts or clusters can make sampling more practical. Then we could select 1 or more clusters at random and perform a census within each of them. This sampling design is called cluster sampling. For each cluster fairly represents the full population. Clustering sampling or cluster sampling will give us an unbiased sample. Okay? So cluster sampling is not the same as stratified sampling. We stratify to ensure that our sample represents different groups in the population and sample randomly within the stratum. Strata is intentionally homogeneous but differ from one another. Clusters, more or less alike, are internally heterogeneous and each resembling the overall population. We select clusters to make sampling more practical or affordable. Sometimes we use a variety of sampling methods together. So sampling schemes that combine several methods are called multistage samples. Most surveys conducted by professional polling organizations use some combination of stratify or clustering sampling as well as simple random sampling. So sometimes we draw a sample by selecting individuals systematically. For example, you might survey every 10th person in the alphabetical list of students. To make it random, you must still start the systematic selection from a randomly selected individual. So there is no reason to believe that the order of the list could be associated with in any way with the responses sought. Systematic sampling can give a representative of the sample as well. Systematic sampling can be much less expensive than true random sampling. When you use a systematic sample, you may need the assumption that the systematic method is not associated with any of the measured variables. So before we talked about different sampling methods, but you could see how when they talk about clustering, one would be by geographic location, right? So state of Indiana, right? So I could do a random sample of the state of Indiana. That's a clustering, right? Because it's heterogeneous. We have all kinds of people in the state of Indiana. But if I were to divide the people into homogeneous, that would be considered stratified, right? And then lastly, the systematic approach would be if I took, let's say I took the phone book would be a great example, but I would say even a list of registered voters, and I chose every 10th person. It's still a little biased because there are a lot of people that aren't registered voters. So you got to find a way to do that, the thing. But the label sometimes doesn't prevent bias, but it can help. The randomization is what really prevents unbiased things. Anyway, so now let's talk about sampling and stuff. So we started this at the beginning of the school year. Remember this? The who, the what, the when, the why, the how. All right. So the who in the survey can refer to different groups, and the resulting ambiguity can tell you a lot about the success of the study. So to start, think about the population of interest. Often you will find that this is not really a well-defined group. Even if the population is clear, it may be a practical group to study, or may not be a practical group to study. Second, you must specify the sampling frame. Usually the sampling frame is not the group you really want to know about. The sampling frame limits what your survey can find out. So if I want to do some sort of survey on health, right, and I sample a bunch of people about their health, the data might reveal something that causes me to take another sample and a different parameter or measure different things. So basically, sometimes a sampling frame can limit what your survey can find out. When I ask you specifically how many times a week you exercise, and I say 1, 2, 3, 4, 5, 6, 7, I'm not asking you what type of exercise you do, how long you do the exercise. Does that make sense? So as soon as I ask the question, I limit the responses. Now I could say, how often do you engage in physical activity? Well, that's an issue too, because some people have different views of physical activity. If I were to walk around the block, I don't think of that as physical activity, where other people do. So that's something they want you to think about. Basically, it all relates to the population. Then there's your target sample. So these individuals for whom you intend to measure the responses, you're not likely to get responses from all of them. Non-response is a problem in many surveys. So we often joke about this with teachers. Ever since Google Forms came out and you could create a survey, teachers and administrators send out tons of surveys. Probably about 10% of the people that receive the survey actually fill it out. So that's not helpful. Finally, there is your sample, the actual respondents. These are the individuals about whom you do get data from and can draw conclusions. Unfortunately, they may not be the representative of the sample or even the sampling frame or the population. So remember we did the project and I said I'm going to share a link to this sample survey that I created for you guys as a template. I shared it on my LinkedIn page. I have 5,000 followers. 3 people filled out the form. It doesn't really represent the population, so that could happen. At each step, the group we can study may be constrained further. The who keeps changing, and each constraint can introduce biases. A careful study should address the question of how well each group matches the population interest. So you always want to look at the data and see if it's a representative of the population. One of the main benefits of simple random sampling is it never loses its sense of who's who. The who in SRS is the population of interest from which we draw a representative sample. That's not always true for other kinds of samples. A valid survey, it isn't sufficient to draw a sample and start asking questions. A valid survey yields the information we are seeking about the population we are interested in. Before you set out to survey, ask yourself, what do I want to know? Am I asking the right respondents? Am I asking the right questions? What would I do with the answers if I had them, and what would they change things if, would they address the things that I want to know? Okay. These questions may sound obvious, but there are a number of pitfalls to avoid. Know what you want to know. Understand what you hope to learn from whom you hope to learn it. Use the right frame. Be sure to have a suitable sampling frame. Tune your instrument, right? So the survey instrument itself can be a source of errors. Too long yields less responses. That's just an example. So if I send a 50-question survey, somebody's going to go, nope, not today. And if I'm only interested, I'm not going to be interested in 50 things. I really should only be interested in 2 or 3 things at a time. Ask specific rather than general questions. Ask for quantitative results when possible. Be careful in phrasing questions. The respondent may not understand the question or understand the question differently in the way that the researcher intended. A lot of times when I take a survey, they ask me a question and I think of a better question in my head and I go, man, I don't know how to answer this because I want to convey a message or information. Even subtle differences in phrasing can make a difference. So just be careful in phrasing the answers. It's often a better idea to offer choices rather than free response. If I say physical activity and somebody says, well, I walk out to my mailbox, does that count? Doesn't help. It's better to say, do you walk 10 feet? Do you walk 100 feet? You know, it's better to have some sort of quantifiable thing. The best way to protect the survey from unanticipated measurement errors is to perform a pilot survey. So you do a survey of a survey, right? The pilot is a trial run of the survey you eventually plan to give to a larger group. You could start with free response, see what some of the responses are, and then narrow it down, so on and so forth. Who you're going to sample, blah, 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 blah. Lots can go wrong. In voluntary response sample, a large group of the individuals is invited to respond, and all who respond are counted. Voluntary response samples are almost always biased, and so conclusions drawn from them are almost always wrong. Voluntary response samples are often biased towards some with strong opinions, somebody who feels the need to voice their concern. Those 3 people took the time to fill out my survey because they wanted me to know something. Bias, right? Since the sample is not representative, the resulting voluntary response bias invalidates the survey. In convenient sampling, we simply include the individuals who are convenient. That might be like a geographic location, but as I mentioned before, one town may be conservative while the next town may be liberal. I might just sample people on my block, okay? That's a convenient sample. Under coverage, you don't get enough people that represent the population. Bad framing, similar situation. Watch out for non-respondents. That's a common one. Sometimes the people that don't respond are the ones that you need the information about. Don't bore respondents by going on and on. A survey that's way too long, people will give up. They won't even read the questions. They'll just submit answers. So you got to be careful about that because that throws the data off. Hard work to avoid influencing responses. Response bias refers to anything in the survey design that influences the responses. If you word the question wrong, would you consider yourself a hard worker or a lazy worker? Well, there's a lot of people in between. So if I'm going to choose, I'm not going to say I'm a lazy worker. And we have to think about biases. So we always look at the data, how it applies to the population, and then we could do things like test pilot things and stuff like that. And I'm going to stop right there with what we've learned because the bell's going to ring in a minute. But basically, essentially, we have to collect the data in a way so that when we use the data, it's helpful. Okay? And that's why it's so important to figure out how we collect the sample data. Okay? That's it. Any questions? All right.